And I think we all understood after this keynote and fireside chat what quantum computing is about, that it's about a lot of, well, brain or power, computing power, and that it definitely is a cutting-edge topic. Nevertheless, what's the status quo in the industry, and what are actual use cases, and which direction are trends moving into? Professor Dr. Frank Wilhelm-Mauch is a theoretical physicist, and after his PhD at the KIT and stays at the TU Delft, LMU Munich, and a professorship even at Waterloo in Canada, he then moved to the Saarland University in 2011 and is seconded in Jülich since 2020. His research is on theory, modeling, and applications of quantum computers. He's the coordinator of the EU flagship project Open Source Q, and he also is a frequent educator on this field, whether it is among tech entrepreneurs, but also to the general public. And he's going to answer all these questions about use cases and trends right now for all of us. So please, everybody, give him a big round of applause.
Thank you. Thank you very much for the introduction. That is a much more flamboyant intro than at your typical physics conference. It's wonderful to be here. And I want to tell you a little bit about quantum computing, where the field is, and what you can do with it. Hope the acoustics is OK. The room is quite alive, but let's look there. So this is my title slide. This is a view in Jülich on a nice day. So I want to briefly tell you what makes the difference of using a quantum computer versus a regular computer, which we call a classical computer. Where does it come from, and what are the challenges? Why is it so hard to build a quantum computer? And why do we, when we talk about quantum computers, look at this somewhat steampunky device on this table, which I'm going to show you a little bit next. And then we are going to look at where does the field stand, and if you are looking at commercialization, what can it do for you, and what are we specifically doing around here, where we are right now. So quantum computing is part of a larger framework of quantum technologies. And today we are really focusing on quantum computing, but there are other technologies that use quantum physics for an advantage, including quantum communication, quantum sensing. But today is about computing, and you see it has many levels. We have software, we have engineering, basic science, but also training. So what makes quantum computers powerful? Think about how you buy a powerful computer today. You are, on the left is a very primitive computer. You are looking at how many cores does it have? How many processes can it run in parallel? And in each of these processes, it stores data in registers, and each register at each point in time contains a number, and then you're running an algorithm on that. Fairly simple. In a quantum computer, you're still working with a binary system. You're talking to the system in the language of zeros and ones. But in between, you're using the magic of quantum physics. One of this is that quantum objects can, in a certain sense, be in more than one place at the same time. If you'd go from physics to information, it means that each register, each place of memory, can have more than one value at the same time. So it can store multiple pieces of data at the same time. So if you work on it, you are building a version of an extreme parallel computer. You need one quantum register, and you can process on it as parallel as you want, where classically you need to have a lot of cores. So this is behind quantum speedup. So let's be kind of very clear here what quantum speedup means. Quantum speedup does not mean that we are getting you a processor with a higher clock speed or anything like this. Quantum speedup is about, this is a fairly mathematical statement, how much does it become harder if your problem becomes bigger? That sounds like a pretty academic question, but for example, your information security relies on it. Your information security with HTTPS relies on the fact that if anybody ever gets near cracking that, you can make your code a bit bigger, and then it will be unsolvable again. So you're always winning the arms race against the decryptor. So this hardness, how fast something grows, is really important. So quantum computers change the hardness. When you have a problem where, in terms of the problem size you can solve, you're suddenly hitting a hard wall, and making it slightly bigger blows up your computer, quantum computers can be there to help. So here is a kind of a cartoon of this. So I don't quite know how the laser pointer works, but here's a cartoon of this, how this could look like. On the horizontal, you have how big is your problem. On the vertical axis, how long does it take? And the black line is the quantum computer, which grows slowly. And the green line could be the classical computer, which is completely optimized. So initially, it's faster. But at some point, you're really hitting a hard wall at which you cannot solve it anymore, and your classic computer goes into chaos, but your quantum computer keeps on running. So there's a caveat, because being in the same place at the same time, if you want to observe this, there's a random result. So that is kind of a mind-boggling piece of quantum physics. This is obviously not, a school lesson, but what this means essentially is that if you program it parallel, you need to make sure that in the end you get a meaningful result. And so which means that quantum computers are hard to code. To use the quantum parallelism requires the right algorithms. But fortunately, those have been discovered. And here are all algorithms that have very, very abstract names that are typically in the machine hall of IT. Combinatorial optimization is such a problem. It turns out many things that keep our supercomputers busy today end up being very difficult optimization problems, but you are calling them finding a route. You are calling them managing a map. You are calling them optimizing an airport. But what takes time is optimization. There's machine learning, artificial intelligence, and other problems. So if you want to use quantum computers, a good way to approach this is to see whether the problem, the use case you have, actually, in the end, is related to one of these use cases. This is a typical way to approach it. Don't try to discover new algorithms. That is very difficult. So this is what quantum computers can do. Now, where do they stand? Well, quantum physics is the physics of the smallest pieces of the world, of our microscopic universe. And we now want to build a computer. We just don't want to observe it, we want to build something. And there's two ways to do this. One is we take small particles like atoms, ionized atoms, we are trapping them in a big machine as seen on the left, and you try to manipulate them. The other approach, and kind of my favorite approach, is you are taking a computer chip like the one shown on the bottom right, and you try to make it so small and so well protected that it becomes quantum. And this is what we're doing in Jülich. You see a picture of the quantum computer we're building in Jülich here, and here you see a model of its central piece. And you see this kind of steampunky setup with these gold-colored plates. So you're seeing this because we need to isolate the quantum computer from external disturbances really well. And this is sitting in a cooled pot that gets colder as you get lower. So the lowest part here is the coldest part. These plates are made out of copper because then they have all the same temperature. You know, if you have fancy cookware, that copper is conducting heat really well. It's gold-colored, so it reflects thermal radiation. The quantum chip is sitting at the bottom, and then around this you see the input and output system, and you see the wiring system, and we have a booth close to the entrance where you can see this even better. So you still see that this is a somewhat experimental device. It's going from the lab towards production. and we have 2 platforms, and that sounds bad, right? We think that we know how computers look, but actually it's not so bad. Just look back at computers of 50 years ago. People made computers out of relays, out of vacuum tubes, out of discrete transistors, where instead of a chip, they needed to solder everything. And just because the physical shape of the computer changed doesn't mean it's a good computer. And in fact, keep in mind that Alan Turing, the Albert Einstein of computer science, worked with a primitive mechanical computer like the one on the top on the middle. And this is, so we are in good company. So these are the types of qubits that you are seeing inside this model here. On the right, you again see our cooling setup. This is sitting next to a lot of electronics. And on bottom, you have your chip, which is sitting on a chip holder. And what you have on the left is a zoom up on a single quantum element. This is made out of a superconducting material. It's actually very simple material. It's aluminum, something we know. It is cooled to very low temperatures. And on the upper left, you see a crossing between 2 wires. This is called a Josephson junction, and it plays for quantum computing the same role that the transistor is playing for classical computing. And in this model, this is all part of the chip that you're seeing on the bottom. Now, how useful are these things? If you look at the media, oftentimes we have this race, how big is the quantum computer? And I will comment on what this means. But we should still keep in mind this is very fragile. Nature really, when we work with it, doesn't want to be quantum. We need to protect it very well. So currently, quantum computers are limited not by how big they are, but by the errors they make. They have an error rate of 0.1%, which means you can do a bit of about 1,000 steps, which is clearly too little. So when people put their applications on quantum computers, they typically work with between 7 and 12 qubits within a larger chip. And to really lower the errors, we have to work hard to improve the whole system, to engineer better materials, and to make a better setup. But again, currently we are mostly limited by errors, but we have clear routes to make this better. So where are we now? We are now in something which is really exciting, which we could call the era of early quantum supremacy. Because you have heard that a year and a half ago, Google has announced that they have done something on a quantum computer that no classical computer would be able to do in acceptable time. So what they have done is they have used a system with about 50 quantum bits and realized that the quantum state of this contains so much information that the biggest supercomputer in the world doesn't have enough memory to store it. It has to put things on the hard drive, and it becomes immediately extremely slow. So with only 50 qubits, because you need 2 to the 50, exponential function, we're very familiar with this during the pandemic, is a number that is too large for classic computers to handle. But they have done this with what people call a synthetic benchmark. So they have tested this under very idealized conditions. Now, if somebody gives me 1,000,000 qubits with very low error, I can do a lot of great things. But what we currently need to find out is what we do between 50 and 1,000,000. Make applications a lot less demanding and make quantum computers better. So what does this mean for users? If you want to play with quantum computers, what can you do with these machines? First of all, you always need to connect them to a great classical supercomputer. So everything where you don't need the quantum computer, you're not running on the quantum computer, you're making it a co-processor. This way, the error rate is not killing you. And secondly, you look for the right applications. One of them is better chemicals. For example, it turns out that plants do something very easily for which human beings need large factories that create a lot of carbon dioxide. And all it would take for human beings to imitate this would be to understand this molecule, which is actually quite small, but is completely out of reach of classical computers. So if we can solve these with quantum computers, we are in good shape. And this is probably the first useful application we will have. Another problem is managing airports. where you need to optimize which planes you use for which route and where you put them, and you want to get the solution quick. You want to be able to update this in the middle of the day. You don't want to step Düsseldorf Airport for an hour to wait for your computer until we have figured out the gates, which is why this is currently still done by hand. Or you want to make mechanical engineering. There's a technique called finite elements, which is a nice method, but it's takes way too long to be practical. And I have heard 2 hours ago that we have won a project to bring this to quantum computers. I'm a bit time aware, so I'm going a bit too fast, but you can ask me more about this. Because in the last minutes, because I believe I have about 2 minutes left, I'm looking at the host, and she is friendly and nodding. Let me point out what we are doing close to here, about an hour away. So we have our project Open SuperQ that was already mentioned. We have been extended until beginning of next year. And it's a first attempt to make a quantum computer in Europe. It's a conglomerate where the key heavy lifting of quantum is still done in the public sector by universities and research centers. But companies are helping us already with all this. Jülich has done that for you. And you can pick and choose, and you also get help from them. This is called Unique, and this is going to open in about a year. This is very well integrated in Jülich's supercomputing system. And our plan is to, as the next level beyond Open SuperQ, is to go one size bigger and do it all in Germany. This is a collaboration between us in the Rhineland and collaborators in other places. And it's again a public-private partnership because we are still at the point where the core quantum stuff is mostly done in the academic sector, but applications and tools are made privately. I've went a bit too fast, I've used too much time, and thank you very much for your attention.
Thank you very much. This was really interesting. You're quite an expert. Really great. And tell me, how often do you meet with other professionals from that industry, with experts in quantum computing?
Online meetings almost daily, of course. But what's really interesting, you know, I've been doing this for over 20 years. And it started about 5 years that I'm not just hanging out with other academics, but that I'm talking with people from startups, with users. And this is not only exciting, it also gets a new perspective to the field because people are thinking about applications and solutions we have never been thinking for. You know, Alan Turing, the Einstein of computer science, much more intelligent than I am, has not invented the fact that we're sending cat pictures around the internet and many other applications. So this is, yeah.
And what kind of companies or what industries are most ahead? Is it the automotive industry or what industry? And then what specific brands and companies?
So definitely the automotive industry is very strong. Companies who are looking to use quantum computers are typically companies that are, for who it's important to have a competitive advantage in IT. And certainly chemicals and material science, because they have a very obvious use case. But we are running a consortium that is coordinated in Jülich with all the 3 big German car companies who are specifically looking at getting things like real-time AI. So AI problems that classical computers, because quantum computers are still small, that classical computers could in principle solve, but they would really take too long.
Okay, and if we want to look at some specific companies, I mean, do you feel like it's more a push from the public and the industry so that companies say, oh, okay, yeah, we have to look into it and we're going to do it? Or what kind of company is actually pushing it forward more actively? Can you give us a specific name?
So, you know, I grew up close to Stuttgart and I got completely justified when Daimler approached me that they had done all their due diligence of that they could do on their own on quantum computing, and then talked to me. But with them, we work with all car companies. We're also very happy with chemicals companies. BASF was early, but close to home. Bayer and E.ON are also currently really embracing this field. So, and for chemicals companies, it's very natural, because in their modeling groups, they are already employing people with quantum training. So there is a very good shortcut to quantum computers.
Really cool. Thank you so much for your insights. It was really interesting. And now please give him a last and big round of applause.
Thank you.
Thank you so much for being here.
Thanks.